All yours.
Okay, thank you. Thank you for coming. Um, First of all, I would like to thank Mutu and Monkey for letting me speak here. Today I'm going to present this paper that appeared last month with Max Bisna, and it's about non-perturbative corrections that appear in minimal supersymmetric theories, in this case in 4D n equals 1 effective field theories of gravity. So I will start the motivation of this talk with the Swampland program, which is about getting the consistency conditions that we want for effective field theories of quantum gravity. The basic idea that you all probably know is that you have an infinite set of possibilities of effective field theories, and only a subset of them can have this UV complete, can be UV completed. What I would like to stress in this talk is that the non-perturbative corrections are essential for this distinction between the two sets. And that is because the non-perturbative corrections in some regimes in the theory are going to test the UV of the theory. That is simply because whenever I go to small volumes, we are used to in a string theory that we have instanton corrections coming from D-branes, from the worldsheet, etc. And also the small volumes are going to probe the UV theory, such that the non-perturbative corrections are going to test and are going to check what is the consistency that this theory has in the UV. So this is something that we know and we understand better in theories with extended supersymmetry. So let me take, for instance, a type 2 string theory on a Calabi-Yau threefold, and we know that there are some specific points in the moduli space in which you have conifold transitions, which are some transitions you can do in a conifold, and it's important to have control over the non-perturbative corrections. So conifold transition is essentially the idea of you take a volume that is parameterized in the vector multiplet. In type 2b, it would be a 3-cycle. You shrink that volume, and then you blow up a 2-cycle in type 2b that is parameterized by a hypermultiplet. And the idea is that by doing this extremal transition, you change the topology of your manifold, and you can see here that you change the Hodge numbers of your manifold such that you transition from one Calabi-Yau to another Calabi-Yau. What I said and what is important is that in order for this to be possible, I have to take into account the non-perturbative effects. So if I would like to go from the Coulomb branch, this part here, to the Higgs branch, I would have to integrate in a D-plane in the theory. This is the usual Strominger story of the conifold transition, such that it regularizes the singularity and allow me to transition to the Higgs branch. If I want to go from the Higgs branch to the Coulomb branch, I would have to take into account different instanton corrections, such that correct my metric and allow me to transition to the Coulomb branch. This is what was understood in this paper by Aguri and Baffa in the 96. So this is the geometric interpretation and how the non-perturbative corrections enter in this theory. But I can also understand this transition from the moduli space point of view. So the idea is that I have a moduli space of Calabi-Yau 1, I have a moduli space of Calabi-Yau 2, and thanks to these conifold transitions, I have a small bridge in which the non-perturbative effects are allowing me to transition from one moduli space to another. So thanks to this, I have a notion of an extended moduli space, of a complete moduli space, whenever I take into account these non-perturbative effects. So the natural question would be now, what happens when I have less supersymmetry for the n equals to 1? So first of all, I am lacking of factorization because I no longer have vector multiplets and hypermultiplets. I have chiral multiplets. I also don't have mirror symmetry techniques that allow me to track the corrections. And I am also having more corrections because I am less protected by supersymmetry. So this is a very challenging task to do in general. So what we are going to do here is to implement a strategy, which is look for sectors with enhanced supersymmetry. And from then, we are going to predict some non-perturbative states or non-perturbative effects. So the question that we are going to ask ourselves is the following. I'm going to look at a sector with enhanced supersymmetry. And from then, I'm going to look at the perturbative spectrum. If the perturbative spectrum does not resemble the one of a theory with enhanced supersymmetry, therefore I'm in a contradiction in the perturbative regime. And therefore I can predict missing non-perturbative light states that are going to complete and extend my moduli space. In the same way that I showed you before that you have this extended notion of moduli space. So in the following, I'm gonna warm up in 6D n equals 1,0 to tell you how the story goes. And this is some understood example from the literature. And then I'm gonna go from the 4D n equals 1 example that we discussed in the paper. Okay, so let's start. I want to consider 6D n equals 1,0 super theories. In this case, I'm gonna take F0 in Calabi-Yau threefold, elliptically fibered, and I can consider the base Fn such that I know what is the heterotic dual of that. The heterotic dual is in E8 times E8 on K3 with the following instanton number. And note here that this n is the same as this n, such that this is how the duality maps from a F theory to heterotic. In this kind of theories, I have anomaly cancellation that is going to constrain the different supermultiplets that I have in the theory. And what is very interesting about this duality and these theories is that in this paper was understood that there is the theory n equals 2 and the theory n equals 0 are connected. So there is a transition that you can do from F theory on this Calabi-Yau to F theory on this Calabi-Yau, or in the heterotic perspective, I can connect these two theories with different instanton number. In the same way as I told you before that you have this extended moduli space, you can transition from one theory to another. How this happen? Well, from the heterotic perspective, it is more difficult to see because you have to go through these small instanton transitions, and these are extremal transitions that you should do, and therefore it's strongly coupled and more difficult to see. But from F theory, things are smooth, and we will see in a minute how you can go from this theory to this theory here and see this notion of an extended moduli space. Okay. So let's start in F theory in this Calabi-Yau, compactifying this Calabi-Yau, F theory in this Calabi-Yau. And I consider a degree 24 hypersurface in this manifold such that I get the following supermultiplets in the theory. It's interesting to note that whenever I plug this number into the anomaly cancellation condition, the equation is off by 1. And this is weird because this is telling you that the theory that you are taking is anomalous. Of course, this is not what is happening, and it was very, very nice explained in this paper that you are missing a hyper, and you are missing a hyper that they denote a non-polynomial deformation. So this hyper, you can see that is in your theory whenever you load down a -2 curve in the base F2, and you get this singular geometry, and from this geometry, you turn on a wave to this deformation. And this deformation is the missing hyper that you don't have, you were predicting by the anomaly cancellation. This also explains the very nice transition between the two theories, because you can check that whenever you turn on this bev here of this hypermultiplet, then you move in a direction in the moduli space in which the topology of the base is now F0. And therefore, you smoothly transition from F2 to F0, where F2 is F theory on the first Calabi-Yau and F0 F theory in the second Calabi-Yau. And this is the notion of an extended moduli space from this perspective. But so this story is very nice, and you can see that there was a missing hyper coming from this non-polynomial deformation. But I am interested in talking about supersymmetry enhancement, as I told you before. So there is a nice way to argument that this missing hyper can be predicted by using these ideas of supersymmetry enhancement. And the idea is the following. So I take the base F2, I compute anticanonical class and the different intersection between the different curves. And I can compute the intersection between the anticanonical class and H, the curve H, and that is 0. What does it mean? It means that in the type 2 language, the H is not intersected by the O7 planes, and therefore I should expect to have enhanced supersymmetry. This was understood by Witten in the 96, very nice explained, in which if you look also the vicinity of H, the geometry looks hyper-Kähler. The dilaton does not vary, you have like a trivial fibration, and therefore you should consider that locally you have more conserved supercharges. And this explains this missing hyper that I was telling you about, because if my theory locally should resemble 60 n equals 2,0, because I have enhanced supersymmetry, I am no longer in a theory with locally 60 n equals 1,0. Therefore, I need a hyper that in combination with the tensor is giving me the matter multiplet in 60 n equals 2,0. And this is the way in which you can predict this hyper. So what we have learned from this example is the following. We have learned that supersymmetry enhancement is important to predict. And thanks to this prediction, some of these degrees of freedom are related to geometry, such that I can deform the geometry by going from one theory to another by changing the internal manifold. And not only that, because thanks to these extra degrees of freedom, extra geometric degrees of freedom, I have this notion of an extended moduli space that I've been telling you about. So in the following, I'm gonna play the same strategy, but in 4D instead of in 6D. And I'm gonna look for sectors that also does not intersect the U7 planes and should have this enhanced supersymmetry locally. Okay, so let's do that. In order to do that, I consider F theory on a Calabi-Yau fourfold such that they have 4D equals 1. And I should look for a sector, so elliptically fibered, and I should look for a sector in the base such that has enhanced supersymmetry. Therefore, I should look for holonomy SU3 instead of SU4. And I'm going to take a curve, as in the previous example, that does not intersect the anticanonical class, and therefore in the type 2 language does not intersect the U7 planes. Moreover, I'm going to take a curve that can be shrinkable, can be decoupled from gravity. And among the different possibilities of the normal bundle, I'm going to take the one with -1, -1, such that is floppable. And I can do these kind of things. But before going to F theory and tell you what F theory can teach us about these sectors, very nice sectors, let me go to type 2B and see what type 2B teaches. So if I take the type 2B limit of this picture here, I am in a sector in which I have a curve that is shrinkable, have the normal bundle of something like a conifold curve that I can shrink it to a point, and I am far away from the O7 planes. It means that this curve locally should resemble the theory of a 4D n equals 2 theory in the sector of the Higgs branch, because I am in type 2B and I have a 2-cycle. And forgetting about the type 2B limit and the orientifold, whenever I have a 4D n equals 2 conifold setup in the Higgs branch, I have a hypermultiplet given by the curve and a massive vector multiplet 5,3. The thing is that, of course, I am in the type 2B limit of F theory, and I have an orientifold projection such that the hypermultiplet goes into a chiral multiplet, and the massive vector multiplet 5,3 goes into a massive vector multiplet 3,1. But there is some inconsistency here, as in the previous case. And that is because I am assuming that I can put far away the O7 planes, I can smear and I can tame the supersymmetry breaking effects as much as I want, such that my local theory should resemble a one of supersymmetry enhancement, but the perturbative degrees of freedom of type 2B, it seems that they do not rearrange in 4D n equals 2 language. And therefore, from this perspective, I can already predict that there are some missing degrees of freedom that whenever I take them into account are going to fill out a hypermultiplet and a massive vector multiplet 5,3. Therefore, I need a chiral multiplet here and 2 chiral multiplets here. That what is important to note is that I don't see in the type 2 perturbative description, and therefore I should go to F theory to try to see if they are there. So from now on, I'm gonna set up a chiral counter because the rest of the talk is about finding these chirals that I need to fill out this 4D n equals 2 supermultiplet. And before going to F theory, let me say also that what I told you about is that whenever I have this supersymmetry enhancement, I have some extra degrees of freedom that are related with geometry and how geometry is gonna change from one theory and from one part of the moduli space to another part of the moduli space. So it is very instructive to check in F theory what are the different geometric deformations that I can do to the curve. And from these geometric deformations, see what are the new degrees of freedom and check if they are the ones that allow me to have to have in the chiral counter 3 out of 3. Okay, so let's back to F theory. I can study the non-perturbative phase of C0, the curve, and there is a natural candidate as a geometric deformation that is called aberrational factorization of the flop. That simply means that I have a curve and I blow up an exceptional divisor. And from this exceptional divisor, I can go back to the curve or I can go back to the flop curve such that I have an extra degree of freedom there. This geometric deformation is something that can only be seen in F theory, and that is important. That's why in type 2B we don't see anything else than the chiral and the vector multiplet 3,1. And that is because if you compute the new anticanonical class after the blow-up, this new term is gonna violate the Calabi-Yau condition in the base, and it's something that from the type 2B perspective cannot be seen. It's really non-perturbative. And you can lift it, you should lift it to a theory in order to see this kind of deformations. Okay, so this is the the candidate that we have for the geometric deformation of my local supersymmetry enhanced theory. And from this, let me see what are the chirals that I can get. So the first one is easy, right? Because I have a new exceptional divisor, therefore I have a new chiral multiplet that is parameterizing the volume of this new divisor. So the chiral counter now updates to 1 out of 3. And the second one, you have to take into account how the Euler characteristic changes, because whenever you have these geometric deformations, the Euler characteristic is going to change. You can compute it and you can check that H11 changes by 1. This is something that we know because this is this extra chiral, this extra Kähler modulus. And H21 also changes by 1. And this is part also of the local data that in F theory comes from axioms. So thanks to this, how the geometry changes and checking these two things, we know that there are going to be 2 extra chirals that were invisible in type 2B, and now they can be explained by this geometric deformation, such that the new chiral counter now is 2 out of 3. And you can also check that, well, I don't have time to discuss this in detail, but you can also check that H31 also changes by this number. What we are getting in the paper in detail is that this is part of a global data. This is part of a decoupled sector. And it is related with the fact that whenever I do this kind of deformations, I have to put the space-time field in D3 branes to satisfy the tadpole equation. Okay. And let me go to the last chiral. How do I find the last chiral? The last chiral is going to be very similar to what happened setup in 14 equals 2. And it's going to come from D brane states. So in the conifold, we are in 14 equals 2, and the states are D3 branes wrapping 3 cycles. Here, what we have is D3 brane wrapping one of these 2 cycles. And what we argue is that the excitation of these D3 strings is part of the missing chiral, is the missing chiral. So these D3 strings are not exotic, it's something that we know that they have been studied in the literature. They have the following normal bundle, and these are cosines of the E strings, such that because we have this -1 here that resembles these E strings. And you can do more. You can compute what is the tension of these D3 strings. And it turns out that they are always tensionful all the way. But this is very interesting because thanks to this, we can have an analogy to what happens in heterotic string theory whenever I go to special points in the moduli space. So we know that in heterotic string theory, there are some special points. Usually there are some self-dual. I have gauge enhancements such that I go to SUN. Here the idea is very similar. I have a tensionful string, and whenever I go to a special point in the moduli space in these supersymmetric enhancement points, I have finitely many massless excitations. And one of them is the chiral that is going to do the job. I have to say, as an important caveat, that I don't know what is the full quantization of this D3 string. But our argument goes as the consistency of the physics, such. Let me say something else. Let me say that I haven't talked about supersymmetry breaking effects.
Gonzalo? Gonzalo, actually, for the
Yes.
last few seconds, you got stuck. So maybe if you can repeat what you were saying,
Sorry.
sorry. And also, we have 5 minutes left.
Okay. Second. So I did I say that we got the three chirals?
I think it was just arriving there. Maybe you were still on the
Okay.
previous slide.
Yeah. Okay.
You were still on
So
the previous
wait.
slide. So
So here are. Oh, okay. Well. Something that I talked about is about the supersymmetry breaking effects in this talk, and they are important, of course. So, for instance, because we are in a theory that the gravitational part is 14 equals 1, I am in a local sector that resemble 14 equals 2, but there are gonna be some coupling with gravity such that it's gonna break or it's gonna modify my physics. So if I consider there are two options, I can consider a non-compact base in the Calabi-Yau fourfold. If I do that, I can push away the supersymmetry breaking effects, and therefore everything that I just said before is gonna be like that. It's not gonna be modified by the coupling with gravity. But of course, if I consider as a base something compact, as I should, then I have a coupling with gravity, and we know that the coupling is related with the volume of your internal manifold. The relevant control parameter is going to be those chirals that appear in the related with the geometry of movable divisors. Because I can put D3 branes on them, I can wrap them, and I have D3 brane instantons that are going to enter in my local theory if these T are not big enough. What happens, and what we discuss in the paper, but I don't have time here to discuss it in detail, is that if I look at the supermultiplet that has 14 equals 2, whenever these guys enter into my local theory, it's going to split the supermultiplet in two pieces in the language of 14 equals 1. And this is how this supersymmetry breaking enter in my local 14 equals 2 theory. Okay, so let me summarize and conclude. From the field theory perspective, what we have seen is that we have put ourselves in a setup in which we have an inconsistency, in the sense that we are in a setup with enhanced supersymmetry, but it seems that the light degrees of freedom in my theory, the perturbative degrees of freedom in my theory, does not rearrange in a 14 equals 2 way. Therefore, I can predict that I have new extra non-perturbative states that are going to do the job. And they come easily, they can be explained easily in this F theory perspective. But this is the field theory perspective. The geometric perspective is this one, such that from the type 2B perturbative description, these kind of deformations are of very non-perturbative origin. And from F theory, these kind of deformations are natural and smooth. Such that I can understand now better this notion of this extended moduli space. This is the figure that I showed you at the beginning. And from the type 2B perspective, I'm connecting two different patches of moduli spaces that they seem to be very disconnected at the very beginning, but thanks to these non-perturbative effects, they can be connected. And I have this extended moduli space. So an open question, and with this I conclude, an open question that we have, of course, and we would love to know better, is what happens in genuine 14 equals 1 setups. So we have studied 14 equals 2 or theories with sectors with enhanced supersymmetry in 14 equals 2, but when we are in a sector with genuine 14 equals 1, I don't have enhanced supersymmetry nor anything, how this story changes. Our guess is that everything is gonna mix. What I told you before that H31 is a decoupled sector and the space-time field in D3 branes are a decoupled sector. What I would imagine is that everything is mixed up and it's gonna be more difficult to track it down. But it's something that we hope to see in the future. And with this, I conclude, and thank you very much.
thank you very much for the very nice talk. So, any questions for Gonzalo?
Actually, I have one. What do you mean? I'm still confused as to why you cannot see the new degrees of freedom in type 2B. It's a low energy physics problem, so it shouldn't really matter whether or not you're using a type 2B or F theory. And also, I think you mentioned that because in type 2B, the blow-up changes the Calabi-Yau condition, but I don't understand why that matters anymore. Because you're using the basically in a way, in the weakly coupled description, you're using Calabi manifold, although I don't
Yes.
think you really want to stay in the weakly coupled description. But as soon as you go to the Calabi manifold, the manifold doesn't have to be Calabian anymore. The canonical class of the manifold is not trivial anymore. So why do you have such a restriction?
Yeah, no, very good question. So the idea is that we put ourselves, we are in a 14=1 setup in F theory, and we put ourselves in a regime, in a local sector in which the fiber over the base is trivial, and therefore I should resemble some theory like if I don't have orientifold, because the orientifold effects, I can put them far away from my theory. And therefore, I can assign the perturbative degrees of freedom that I have there. But there I have an orientifold projection if I am in type 2B. Therefore, I don't get the degrees of freedom that I should have in a 14=2 setup. And what we argue is that this is something that can only be seen in F theory, because in F theory there are some geometric deformations that cannot be seen from the type 2B perspective. It's only that there are some geometric deformations that if you want to study type 2 Calabi-Yau orientifolds, or even type 2 Calabi-Yau, are difficult to know what are all those non-perturbative. So these deformations are of non-perturbative origin, and therefore are more difficult to track down what are the degrees of freedom and what is the physics. I think it
Sorry, I
doesn't
don't really
even convince you.
understand. Yeah, maybe I'll ask you more later.
Okay, perfect.
Okay, so if there are any other questions for Gonzalo, this is a good time. Okay, I see no hands. So, I mean, of course, we'll ask the speakers to stay back for a few minutes after both the talks so that people can discuss. But thank you very much, Gonzalo.
Perfect. Okay.